Okay, so here we go. Last time we were talking about different ways to relate functions to pictures. So it said different ways to represent functions geometrically, right? And so I made this observation that graphs are what we're familiar with. That's what every picture you draw, practically every picture you've drawn in a single variable calculus class is a graph. And so it's tempting from that experience to kind of conflate the word picture with the word graph, and you gotta not do that anymore. That's importantly confusing. So as an example of the importance of the distinctions and how they work, look at this example here. By the way, for your consideration, I've written multiple past midterm exam questions with this exact example in mind. You'll find them very easily if you look through my old midterm exams. But anyway, something to think about. So in this question, we have a line, L, like this, and there's the equation, right? And the question is, what functions relate to this picture? Right, so for which function is this the graph? For which function is this a level set? Which function parameterizes this line? Right, so this one geometric object relates to a bunch of different functions by way of these different constructions. Okay, so let's think about how the details work here. So this is a graph of this function right here, I claim. Now, you might look at the algebra that was given and then the function whose graph it is and notice that they're not the same. They're importantly different, right? So, now, what gives me the right to say that this line is the graph of this function? Well, keeping in mind what a graph is, graph says that if you set that function equal to a new variable, let's say y, right? Graph means what you get as a result of setting that function equal to that new variable. And how do I know that this is the same as the line? Well, because these are algebraically equivalent. You can just fiddle around trivial high school algebra, turns the green equation into the blue equation, or vice versa. Take your pick. How we doing? Is everybody by it? Okay. All right, so that's the first function. And let's see. Oh, by the way, how would I find this function? I presented to you here as I just pulled it out of a hat. How would you find it in practice? Notice that all I've done here, going from the green to the blue, is I've done perfectly legal and reversible algebraic operations in which I isolated y on one side of the equation. In other words, I solved for y. Right? In this action of solving for y. By the way, in this class, when I say solve for one of the variables, I mean as a function of the other's variables. Right? So not finding all possible values. Right? Solve means that one of them is explicitly a function of the others, and functions only have one value. Okay. So anyway, solve turns it into a graph. Okay. All right. Now let's look at the next function I claim relates to this line. Same line, and that is this function right here. I claim that this line is a level set of this function. Now, how do I know that it's a level set of this function? Well, keep in mind what a level set is. A level set is what you get when you set your function equal to a constant. So if not 0, excuse me. If I set it equal to 6, right? Now this is making a level set, right? The act of setting a function equal to a constant makes a level set, and easily confirmed, this is, of course, equivalent to that. In fact, it's identical. Okay. Everybody happy? Question?
Why do you switch from R1 to R2?
Well, that's just the nature of these functions. I mean, you can just look and see this function right here X is the only input variable. Y is what we choose to call the output values as part of the process of forming the graph. But other than that, there's only one actual input variable. Does that make sense? Whereas if you look at this function right here, there are literally two input variables. So the domains are two. Yeah. Okay. All right. So before we go on to the third, let me point out this is already, I think, a pretty dramatic example of how, these are two totally different functions. And as you observed, with totally different domains even. Right? Completely different functions that both describe that line. Just in different ways. It's the graph of one of the functions. It's a level set of the other function. So in practice, why do we care about this? Well, because we're going to be interested not just in lines, of course, but in geometric objects. For example, this line, and wanting to draw certain geometric conclusions about it. And calculus is a handy tool for doing that, right? As y'all recall from Calc 1 classes. But specifically, there is a calculus of graphs, namely, what do the algebraic objects like derivatives look like in the graph context? And then there is an entirely separate calculus of level sets, namely, what do these algebraic objects, namely various derivatives, what do they look like in the level set context? And what things look like in these different contexts is just totally different. So if you want to draw a conclusion from the calculus of graphs, you'd better use the function whose graph is what you're interested in. And if you apply the calculus of graphs to this function down here, you're going to get some absolute garbage nonsense. Because square peg round hole, or however you want to say it, is you're using the wrong. You're making the completely invalid interpretations from what you've written down. So you've got to be really, really careful about this. Now, I will also point out in this example right here, the actual calculations, what a lot of people like to call the math, which is absolutely not. It's just algebra, right? But the algebra that gets you from here to here, or from here to here, or between these two, or whatever you're doing, the algebra is trivial. It was super trivial. It's middle school level algebraic manipulations, right? So that's not what's hard about this example. That's not what's important or interesting about this example. What's important and interesting about this example is the strictly proper interpretation and application of the words, right? What exactly do we mean when we say graph? What exactly do we mean when we say level set? And implementing that appropriately. That's what's important here, right? So something to be careful about. So for example, I mean, if I were to, let's say, forget about this right here. If I were to ask you, well, let me just do it like this. What is the function? Find a function for which a level set is this line. If you write down 2x plus 3y equals 6, that's wrong. That's not a function. That's an equation. Right? So remember, a function is very specifically, it has a domain, it has a target, and it has a rule of assignment that takes an input value and gives you an output value. That's not what this is. This is an equation, right? That says that the left side equals the right side. Now, I mean, yeah, this equation represents a level set of the function, not that one, the function here that we're interested in. It is a level set of the function we're interested in, but I didn't ask for a level set of the function. I gave you a level set of the function, right? I asked for a function. And again, with the idea in mind that I wanted a careful and precise interpretation of the terminology. So this is completely wrong. Make sure you're comfortable with that. And again, as usual, feel free to come to office hours, mine, the other instructors. Don't forget about the help room, ask classmates, etc. But make sure you see why it is that this is completely wrong to a question for which this is perfectly correct. Okay. So lastly, how would I parameterize this line? Now again, that's another function that in its way relates to the given line. I'm sorry, yeah?
So like a level set would be surjective.
A what now?
The level set, so like 2x plus 3y, would that be like a surjective function?
It doesn't have to be. No. Doesn't have to be. So keep in mind, a surjective function is a function whose target is that the entire target is part of the image. Every possible target value actually comes out of the function at some point, which doesn't really have anything to do with the fact that this function here, I just need to set it equal to 6. Right? So I don't really care, what's going on here in the target and whether or not this function fills out the whole target. I'm only interested in 6, really, right? So whether it's surjective just doesn't matter at all. Yeah. Did I see another hand? Yeah.
How do you indicate that the level set is at c equals 6?
Do what now?
How do you indicate that the level set is at c?
Oh, well, the way I phrased the question, you wouldn't have to. The question said, what is the function? Or find a function for which the following holds. Right? And the following is, I want one of the level sets to be the given line. But the question said find the function. It didn't ask which level set is the line in question. Does that make sense?
Yeah.
Yeah. So this is a function for which one of the level sets is the given line. So if that's all the question asks, then that's all you got to give me. Yeah. Okay. Okay, so the parameterization, this is, again, kind of old news. We've parameterized lines before. I'll just point out that there's your x naught, and that gives rise to this 2. And here is your difference vector, aka your direction vector, and that gives this 3 and this minus 2. And, x naught plus tv, etc., and you multiply it out, and you'll get this. So you can fill in those details. But again, a different function. Not only does it have a different formula than the other two formulas, but it also has a different domain and target than the other two functions as well. Right? So completely different. All right. So again, it's not about the algebra. The algebra is trivial. It's about proper understanding and interpretation of the language. Okay. Strictly speaking. Okay, so I've already kind of talked through all of this. The whole point of this distinction is that the calculus is going to look different in all of these constructions, and you've got to use the right calculus for the right interpretation. In order to do that, you've got to know what kind of a picture are you looking at, and the calculus of level sets is totally different from the calculus of graphs, et cetera, et cetera. Okay. Okay, moving along. Here is a nice little relationship between graphs and level sets. Very useful here and there. I'll show you an example in a second here. But I claim every graph is a level set. As follows. Here's the critical bit of algebra. This right here. And notice this is another algebraic equivalence. These two equations are completely equivalent. Practically nothing happened here, right? I took the right-hand side, I subtracted it over to the left-hand side. It's basically nothing happened. And yet, I get a really nice interpretation, because notice what had been written as a graph is now written as a level set. That's pretty convenient. If I know the calculus of graphs, but if the calculus of graphs doesn't help me answer the question that I need, if I just convert my graph into a level set like so, maybe the calculus of level sets will be useful. This is all you have to do, right, to make that transition. Now, very importantly, make sure to notice the function here, the function whose graph I was initially interested in is not the same as the function. Missed. Not the same as the function whose level set I'm looking at here. Right? So I'm not saying that the graph of f is a level set of f. Absolutely not. The graph of f and level sets of f live in different worlds. They're not even in the same world. Right? But a graph of one function can be rewritten as a level set of this different function. Right? It's very important to make sure when you do this conversion, you've got to identify what is your new function. Notice it has more input variables. Right? F was a function of merely n input variables, x1 through xn. This new function, whose level set we're looking at, this new function has all of those n variables and y also an input variable for this function. So, very, very different functions, but this converts you from one to the other. So here's an example of this in action. Suppose the question is posed to you as that you want to understand the graph of this function here. And notice that's what I have here. That's the graph of this given function f. And suppose the question asks me to determine something geometrically about this graph that the calculus of level sets would totally crush. Right? The calculus of level sets would be super handy. And we're going to find this is going to happen. Right? That what I need might not be what I'm currently set up for doing. If I need to use the calculus of level sets, trivial algebra, again, nothing happened to speak of here in doing this switch. I just moved everything to the other side of the equation. Now, though, very happily, I get to observe that this is now a level set as desired. Not of f, of course. This isn't f equals 0. This is that thing equals 0. So if the calculus of graphs of this function doesn't do what I need, then the calculus of level sets applied to this function might give me what I need. Everybody see how that happened? Okay. Nothing to it. All right. Neat trick. Very handy. Tragically, it only goes one way. Every graph is a level set, but not every level set is a graph. Easy examples. Here is a level set. Right, there's a level set right here. I've got function equals constant. That makes this a level set. It's a level set of this function right here, g. Is it a graph? Can I do some little algebraic trickery and make this a graph? Can I solve, for example, can I solve for y? And, again, there's a different kind of sloppy use of the term solve. Sometimes in high schools, the word solve gets taken to mean find all the possible values. When I say solve, I mean find that variable equal to a function of whatever variables remain. And function means, again, only one value. So can I write y equals and then unambiguous expression of only x? And no, absolutely not. There's going to be two. It's a plus and a minus. Likewise, if I try to solve for x, again, losing. Right? I can't do it. It's not possible because there are multiple possible values. So this is a level set. It is not a graph. And so you are, if we need to use the calculus of graphs here, we've got a problem. And we will actually revisit this dead end in a few weeks. For the moment, we're out of luck. Okay, rotations. So this is a neat trick for helping you understand certain equations of three variables. If you have an equation of three variables, what's the resulting surface look like in general? It's a pretty hard problem. I'm not going to be able to give you an algorithmic, here's how you do it, this will always work kind of an answer. But I can, again, give you tools for your toolbox, and I think this is a really nice one. This only works sometimes. But it comes up surprisingly often. And here's the trick. If, and I emphasize if, this will not always happen, but if x and y appear only in terms of this expression. All right, so I'll show you some examples in a minute. But if this is the only way x and y appear, is as part of square root of x squared plus y squared. So there's no e to the x anywhere in your equation. There's no sine of y cubed or anything like that anywhere in your equation. X and y appear only as part of this form. Then here's the very powerful geometric conclusion. Your surface is rotationally symmetric around the z-axis. So this is another one of these examples of what I like to call kind of like visual freebies, right? Because you can usually at a glance just eyeball and look and see, do x and y appear in anything other than this form? You don't need to do a lot of work in most cases to notice that. It's usually pretty clear at a glance. And then again, immediate, powerful conclusion. So why does this work? I'm going to show you two reasons, or 2 points of view, you might say. One is, let's suppose that I have a point, and then I rotate that around the z-axis to then give me a different point. Now I have 2 points that are rotations of each other. They have different x coordinates. They have different y coordinates, the different points. But here's the thing. That kind of doesn't matter as far as the equation's concerned. The equation x and y only show up as part of this expression right here. And of course, that expression, square root of x squared plus y squared, is the what you might call the cylindrical coordinate r, namely distance from the z-axis. And because these are rotations of each other, different x and different y, but they have the same value of square root of x squared plus y squared. And of course, they're also in the same horizontal slice, which means they have the same z. So as far as the equation is concerned, everything that actually gets plugged into the equation, these points are morally the same. And so either they both work or neither works. All the same arithmetic. So that's one point of view. If you like, here is a different point of view. If you take such an equation and convert to cylindrical coordinates, and think about what would happen if this is, you're plugging in for cylindrical coordinates. Well, everywhere, of course, that you see this, you're just going to replace that with r. Right? Which doesn't have any thetas in it. This is the only way x and y show up. The x's and y's will contribute nothing but various r's into your new cylindrical equation. Then there's also z. What does z turn into in cylindrical coordinates? Well, z. Nothing happens there. Z is already a cylindrical coordinate. And no thetas came up in that conversion process. And you may recall we discussed previously, no thetas means rotationally symmetric around the z-axis. Okay. All right, so I am a big fan of this observation. Let me show you why. It's based on this observation here about rotationally symmetric surfaces. If you have a rotationally symmetric surface, any cross-section in any plane containing your rotation axis is enough to understand the entire surface. Right? If it's rotationally symmetric, and if you know what a cross-section looks like, take that cross-section and rotating it will generate the entire surface. So rotationally symmetric surfaces are really easy to draw in that sense. So here's this collection of observations in action. Let's try to understand this equation right here. You may recall last time I threw this up on the board and said, well, we'll be able to understand pretty soon how to draw this equation, the solution. So step one, X and Y appear only in the proper form. This is rotationally symmetric around the z-axis. Everybody good? If you're uncomfortable, if you're wondering where the square root is, don't forget I can rewrite this as z equals square root of x squared plus y squared quantity squared. And now, as required, x and y appear only as part of that square root of x squared plus y squared. So, perfectly fine. Everybody happy? Okay, it's rotationally symmetric. That means I can look in any cross section containing the z-axis. There's a bunch of planes containing the z-axis. Pick whichever one you like. I'm going to pick the YZ plane, but if you wanted to, you could instead pick the XZ plane. Whatever, it's all good. If you just really want to make your life difficult, you could pick the plane y equals x, I guess. That'd be weird, but if you wanted to, it's perfectly fine, I guess. Whichever one you pick. I'm going to, again, choose the YZ plane, otherwise known as x equals 0. And if I want to know what that cross-section looks like in that cross-section, in that x equals 0 plane, we'll just plug in x equals 0 right into there. And what comes out is z equals y squared, which is a familiar equation. Notice specifically, familiar equation of now only 2 variables. Right? We started with an equation of 3 variables. That was the whole problem in the first place. We don't know how to deal with this. Now we've got it down to an equation of 2 variables. And then we're going to have to play some geometric games. But this, again, old news. It's a parabola, like so. And we know our surface is rotationally symmetric. We know that means all I have to do is take this cross-section and literally imagine it rotating around the z-axis. And so our surface is going to be kind of a bowl thing, about like that. What do you think? Everybody all right? Yeah.
Is there a reason you're doing x equals 0 and not like y equals 0?
Yeah, arbitrary. As I said, you can pick any plane that you want as long as it contains the axis of rotation. I like the YZ plane because I feel like I'm looking right at it. It's not like at an angle somehow, and I just find it easier to look at. But if you want to use my very next example is going to use the XZ plane. But here, no particular reason. I started off with the easy one. Yeah. Oh, yes.
Are there any benefits to ever using the XZ plane over the ZY plane? I feel like right now it looks like the ZY plane is much easier to visualize.
I think so. I don't want to say never because, that's
I understand that. Most of the time.
Yeah, my first instinct is if the z-axis is my axis of rotation, my first instinct is to go with the YZ plane.
Right, cool.
Yep, totally. All right. So a little terminology, by the way, this is called a paraboloid. It's based on the fact that this is a rotation of a parabola, as we just saw. And so terminology that you just have to know. Okay, next example. What do I do with this equation right here? Well, again, x and y appear only in the special form. That means it's rotationally symmetric around the z-axis. That means that it is, this surface I'm trying to understand, is a rotation of its cross-section. Pick any plane containing the z-axis, doesn't matter. Right? And again, just to show that I can, this time I'll pick the XZ plane. The XZ plane, of course, is described by y equals 0. Be real careful about that. It's easy to mess this up. It's easy to look at, well, I'm picking the XZ plane, and then you see the X in what you just said, and then you forget that means it's Y, not X. That's equal to 0. Anyway, Y equals 0. So again, we plug that in to our algebra, and what comes out That cross-section then is just this equation, x squared minus z squared equals 1. High school algebra, right? This is an equation of two variables. Y'all recognize this as a hyperbola, I hope. By the way, I'll tell you what I tell all my classes at this time. I understand Algebra 2 was a long time ago. You might have forgotten. You might be a little bit rusty. You definitely want to brush up and make sure you're good with equations or hyperbolas, because it comes up here and there. So, hyperbola, rotational symmetry. We just now need to rotate this around the z-axis, and the result is something kind of like that. And this is called a hyperboloid because it's a rotation of a hyperbola, just like paraboloid and parabola. Pretty good? Yeah. Well, that's right. So this is the first observation I make up here is that x and y appear in the special form. That means that it's symmetric around the z-axis, and things that are symmetric around the z-axis are literally rotations of their own cross-sections rotated around the z-axis. Does that make sense? Yeah. Yep.
Is it not zero at the origin because it's equal to 1?
Is it what now?
Not like 0 at the origin because it's equal to 1?
Oh, if I understood your question correctly, yeah, this 1 is why this curve does not include the origin. Yeah, right. Right. So, yeah, again, just make sure you're good with all your hyperbolas and stuff. Yeah.
Why is it called a one sheet? What does that mean?
Great question. Yeah, that's going to segue into the next example. So yeah, let me leave the last little bit of terminology here dangling. We'll come back to that. Let's see the next example. Now, in this next example, I'm going to make an analogous argument. I'm going to leave the details of thinking through the claims that I'm going to make as an exercise for y'all. Suggested exercise, you don't have to turn it in. But recall that when x and y appear only in the special form, then the rotational symmetry is around the z-axis. And now I'm going to suggest if x and z appeared only in the special form, wouldn't you guess that would give you a symmetry around the y-axis? Now, that's a fantastic exercise to think through. You're going to draw a picture that looks a lot like this one, except instead of looking at distance to the z-axis, you'll be looking at distance to the y-axis, etc. Right? A bunch of little details to think through. But anyway, that will give you a valid result. And then likewise, if y and z are the two variables that appear only in the special form, then you have symmetry around the x-axis. So there are actually three versions then of this theorem, and I'm going to apply one of those here, looking at this equation. How do I understand what that looks like? And let's see, notice by the way that x and y do not appear in the special form. It has to be only a function of square root of x squared plus y squared. And this minus sign just, it just messes that all up. It's not going to work. Right? There's a plus in front of the x squared. There's a minus in front of the y squared. We lose. So there is no z-axis symmetry. But you notice the easy equivalent algebra makes y and z appear only in the special form. And so we get a rotational symmetry around the x-axis, which is there. Okay, rotational symmetry around the x-axis. Pick your favorite plane containing the x-axis. Again, you have a lot of options. Suit yourself. I'm choosing the xy plane here, but I could just as well have chosen the, let's see if I can draw this reasonably. Pick the xz plane instead if you prefer. It doesn't matter. Okay. But anyway, going with the xy plane, of course the xy plane is described by z equals 0. That makes it easy to see how this algebra works. plug that in. Out comes this equation here. Again, familiar. Only two variables. Hyperbola. Flashback to high school. It's like the 3-point lines there on that little basketball court. And that is a hyperbola that I'm then going to rotate around my axis. Keep in mind now my axis is the x-axis, right? And rotating that around, I get, this is hard to draw. Oh, man. This was my best crack at it here. Use your imagination. These hyperbolas rotating around the x-axis. I like to think of this as being kind of like two contact lenses that are kind of like, I call it the staring contest, right? Because there's two contact lenses that are just like, they're right up at each other's face, you know what I mean? If you want to think of it as cereal bowls that are on their sides, something like that. Anyway, still, it's a rotation of a hyperbola. And thus, again, we want to use the term hyperboloid. And this goes back to the original, or the previous example on this page, which is, we now, you'll notice, have two surfaces, each of which is a rotation of a hyperbola, and therefore each of which wants to be called a hyperboloid. So which one should we call hyperboloid, and which one can't we call hyperboloid because, well, you can't give the same name to two different things. And our solution to that is to just specify this is one connected chunk, right, what we call one sheet, and this is two disconnected chunks. So we call this two sheets. That's the terminology. I forgot who asked that question, but is that, yeah?
Does it go up more than two sheets?
No, these are the only two. Yeah. Okay, moving along. Deformations. So we're going to find that sometimes we need to understand a surface whose equation is not something we've studied before, but whose equation is really similar to something we've already studied before. And so the idea is to take, figure out how to use our knowledge of, for example, this equation. That's an easy one. That's a sphere. You can see it right there in the equation. This just says rho equals 13, basically. The spherical coordinates, rho equals 13. So easy to understand equation. How do I use this knowledge to help me understand this equation? Very, very similar looking, but importantly different. And so how do I mean, if this equation looks a lot like that equation, wouldn't you kind of hope that this picture would look a lot like this picture? And depending on what the connection is algebraically, what does that tell me about what the connection is geometrically? Okay, so that's going to be our goal. Let's see here. We will approach it as follows. Notice that all I did to turn the left equation into the right equation is everywhere I had a z, I replaced it with a 2z. Right, so the question I want to ask first is, what happens to the geometry? What happens to the set of solutions when everywhere within one equation I replace every z with 2z? What happens to the surface? Okay, well, the way I'm going to argue this point right here, 3, 4, 12, clearly works. A little bit of arithmetic. But it doesn't work in this equation over here, of course. The arithmetic's all messed up. In particular, the 3 got squared, the 4 got squared, the 12 got squared, and they added up as they should. Over here, the 3 gets squared, the 4 gets squared, and then the 12 gets multiplied by 2 to become 24, which gets squared. I get totally different arithmetic, crash and burn. Right? Well, okay, this 2 that I put in here messed it up. The arithmetic that worked just fine, now I'm all off track because of that 2. So the rationale that I'm going to give is, okay, let's get clever here. And the clever observation is to think, what if I replace that 12 with a 6? Right? Not that you have to, but let's just play along. Well, what happens if I put the 6 there instead of 12? Well, then the 3 gets squared, and then the 4 gets squared, and then the 6 gets multiplied by 2 to become 12, which gets squared, which is what, in some sense, we saw previously. Right? So the punchline here, then, is that when you do algebraically this, when you replace z with 2z, then all of your z coordinates should get cut in half as a result. Or said differently, your surface should get squished by a factor of 2 in the z direction. That make sense to everybody? Okay. Another way to say this, as I have it drawn here, whatever you do to the variable in the equation, so here I inserted an extra factor of 2 that messed everything up. Well, because of that extra factor of 2, I need to divide the actual z coordinates by 2. In other words, geometrically, the z coordinates get divided by 2 instead of multiplied by 2. It's just balancing what I did algebraically. So that's a pretty good general rule of thumb and a very powerful trick. And notice, having made this observation, I came into this example already knowing this. And then to the question of what does this look like? Oh, okay, well, z gets replaced with 2z. That means that all my z coordinates get cut in half. That means that this sphere that I started with gets squished, and thus I get this kind of flattened former sphere. It's called an ellipsoid, as it turns out. But that's what I get. So my knowledge of a simple equation allows me to understand more complicated equations. Now, a few more examples with which I'm going to be really quick. Let's look at this here. In fact, I'm going to phrase this as, what is that equation? What does this equation represent geometrically? Let's think about our tools. This is a three-dimensional thing. It's not rotationally symmetric around any axis. I do see the x squared and the y squared, but these denominators mess it up. Again, that rotational symmetry theorem is very delicate. It has to be exactly, only, specifically, precisely square root of x squared plus y squared. And this, you just can't rewrite this exclusively in terms of square root of x squared plus y squared. So, I have no rotational symmetry tools that I can use. What am I going to do? And the answer is I'm going to go back to, well, I already understand this. This green one's easy. And understanding that as I do, and seeing, for example, that x just gets replaced with x over a, as I have here. What is the opposite of dividing by a? Well, magnifying, stretching in the x direction, stretching by a factor of a. And so my unit sphere gets stretched outward in the x direction. And then likewise, notice my y gets replaced with y over b. That then is going to involve stretching in the y direction by a factor of b. And z by z over c, again stretching in the vertical direction. So nice punchline then. Just looking at how these algebraic substitutions worked, I get to conclude, I missed, that this is just a stretched out sphere known as an ellipsoid. Is everybody good? All right. Do be careful, please, of the following. Here's an easy mistake to make. let's suppose that the equation had been, here, let me draw a line right here. Let's suppose that the equation had been, x squared over 4 plus blah, blah, blah. And let's suppose that I wanted to relate that to x squared plus blah, blah, blah. So I want to relate this to this. Right? And here, first let me point out what a lot of students will do wrong. A lot of students will incorrectly, with too much focus on the sort of typographical situation, will see, oh, it looks like the x got replaced with x over 4. I mean, again, cosmetically, it kind of looks like that, doesn't it? You'd be surprised how often students step on this landmine. The point here is that, let's see here, what I need to drag this. I have a little bit more room. Notice I can rewrite this equation as x over 2 squared plus blah, blah, blah. Right? So when I say replace this x with something, that means that whatever had happened to the original x, whatever that was that happened to it, has to happen to everything that you replace it with. So this is an example of replacing x with x over 2. It's not about how it typographically lays on the page. It's about everything that had happened to x now has to happen to all of what you replace it with. And so this is actually a stretch by a factor of 2 in the x direction, not a stretch by a factor of 4. Everybody good with that? Okay, a couple more examples. I'm going to let y'all just read these. It's pretty straight stuff. Y'all already know, we've already discussed this is a paraboloid, and thus this is a stretched out version of a paraboloid. This paraboloid had circular cross sections. When you stretch out circles, they become ellipses, so we call this an elliptical paraboloid. So think through the details. Likewise, totally analogously, this is a hyperboloid of 2 sheets previously discussed. Therefore, this is an elliptical hyperboloid of 2 sheets. Okay. All right. I'm going to do one quick thing in the next chapter here just to kind of get it going. We're going to start doing some calculus. We're going to take some derivatives. First thing you need to know, there's multiple kinds of derivatives. It is unfortunately a little ambiguous if you just say the derivative. Which one? There's several. So heads up for that. Realize when the very first derivative I'm going to show you on Wednesday is one of many. And please don't think of it as being the only, because it isn't. There are several others. So just real quick, also, we are going to use the word derivative to refer to these several different things. So the reason that we're using the same word to refer to multiple different derivatives is because they have this very important unifying feature. They all, in their different ways, they all relate input changes that go into the function and the corresponding output changes that result. So be on the lookout for every derivative that we talk about over the next couple weeks. There's always a relationship between input changes and output changes. Okay, good place to draw the line. We'll see y'all on Wednesday. Have a good one.